Welcome to our quantum deep dive. Today, we're tackling one of the biggest questions there is, really. Why does anything exist at all? You see, physics tells us the universe should be totally empty, but, well, clearly it isn't. We're going to dive into a tiny, almost ghost-like particle that might just hold the answer, the antimuon. This deep dive, all based on the work of Gergoet-Schneeppert, is going to take us right to the very edge of reality. So here's our game plan. We'll start with that huge cosmic imbalance, the mystery of why we're even here. Then we'll get to know the heavy twin at the heart of our story. After that, we'll see how scientists are actually hunting for this ghost particle, explore the pretty surprising quantum toolkit it gives us, and finally ask the big one, could this be the key to completely rewriting the rules of the universe? Okay, so before we can really get into the antimuon itself, we have to zoom way out and start with that much bigger question, one that's really at the heart of all cosmology. Right. So according to our very best theories, the Big Bang should have created equal amounts of matter and its exact mirror image, antimatter. Think of it like a perfect cosmic coin flip that should have ended with a universe just filled with pure energy, but, no actual stuff. Yeah, matter and antimatter are like these identical twins, but with opposite charges. And when they meet, poof, they annihilate each other in a flash of energy. So if they were created in equal amounts, they should have wiped each other out completely. But something survived. The very fact that we're here talking about this means there was some tiny, absolutely crucial imbalance in favor of matter. And you better believe physicists are desperate to figure out why. And the key to solving this huge cosmic puzzle? Well, it might just be hiding in the very subtle behavior of one specific family of particles, the real fundamental building blocks of our universe. So let's meet the lepton family. You definitely know the electron. It's the stable little particle that powers basically our entire world. But it actually has two heavier, really unstable cousins, the muon and the tau. For today, we are zeroing in on the muon. It's fundamentally just like an electron, but with one key difference. And that difference is mass. A muon is about 207 times more massive than an electron. Now, this extra heft makes it really unstable. It decays in just a couple of millionths of a second. But it's that very same mass that gives it these unique properties, making it an incredibly sensitive tool for testing the laws of physics. And this brings us to our main suspect, the antimuon. It's the muon's perfect antimatter twin. Same mass, same super short lifespan, but it has a positive charge. The hope is that by comparing the muon and the antimuon with incredible, mind-boggling precision, scientists can find a tiny, tiny difference in how they behave that might just explain everything. Okay, but how on earth do you study a particle that only exists for a couple of millionths of a second? Well, it turns out you have to build some of the most complex, most massive machines on the entire planet just to create, capture, and measure it before it vanishes. You know what the funny thing is? The search didn't even start in a lab. It started on paper. Back in 1928, Paul Dirac's equations basically said antimatter had to exist. Then, just a few years later, the muon was discovered, not made in a lab, but found in the rain of particles we get from cosmic rays. It's really only in the last few decades that we've built the tech to produce them on demand. At places like CERN, scientists pretty much have a recipe. First, they smash a beam of protons going incredibly fast into a target. This creates this whole shower of new particles, including things called pions, which almost instantly decay into the antimuons they're actually looking for. Then, a series of powerful magnets act like a filter, grabbing those antimuons and steering them into a massive storage ring where they can be studied. So in experiments like Muon G2, scientists are looking for a very specific behavior. Once those antimuons are flying around that storage ring, they start to wobble in the magnetic field, kind of like a tiny, tiny spinning top. Now, our best theory of physics, the Standard Model, makes an incredibly precise prediction for exactly how much they should wobble. And the result? Well, there is a tiny but persistent difference between what our theory predicts and what the experiments actually see. This number here, this represents that difference. Now, it might look absolutely minuscule, but in particle physics, a gap this significant is like finding a dinosaur bone in your backyard. It's a huge clue that something is missing from our theories. That little discrepancy is so incredibly exciting for physicists, but you know what? The story doesn't end there. The antimuon isn't just a mystery we need to solve, it's also becoming a really powerful tool for technology, opening up entirely new ways of seeing and measuring the world around us. Yeah, its unique mass makes the antimuon a tool like no other. It lets us make these ultra-precise measurements to test the fundamental symmetries of our universe, to hunt for particle decays that our current theories say should be impossible, and even to pioneer new kinds of quantum sensors. Okay, here's a great example of its power in action. Scientists can create something called a muonic atom by literally replacing an electron with an antimuon. And because it's so heavy, the antimuon orbits the nucleus about 200 times closer. This super close orbit makes it crazy sensitive to the size of the nucleus, and it led to a new, much more precise measurement of the proton's radius, which in turn created its own brand new puzzle for physicists to solve. So, all of this brings us right back to where we started. From its little wobble in a magnetic field to the size of the proton, the antimuon just keeps pointing to these little cracks in our understanding of everything. These precise measurements are doing so much more than just finding new puzzles. They are testing the most fundamental laws of nature. This is a direct search for the very processes that could, finally, explain why we live in a universe full of matter and not just an empty void of energy. And when you look ahead, the ideas get even more visionary. I mean, could we use the antimuon's spin state as a temporary quantum bit, a qubit? Could we store data in those muonic atoms? And way, way down the line, could we ever actually harness the perfect energy conversion of matter-antimatter annihilation? These aren't just science fiction, they're active areas of theoretical research right now. So this tiny, fleeting particle really stands at the very edge of what we know. It connects the deepest question of our own existence to the future of technology, and it promises to unlock a whole new chapter in science.
Male host, we really hope this deep dive, based on the work of Jörg O. Schneeppert, has given you a glimpse into the profound mysteries the antimuon might one day solve for us all.
For more, you should definitely visit schneeppert.de. Thank you so much for joining us.
Schneeppert.de is a private project by Jörg O. Schneeppert dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.